Hello and welcome back to Calculus 1, section 3.11 on my favorite topic, related rates. Finally, a section that we can make money with. All prior to this was just blah, 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 derivative this, derivative that. Computer can do pretty much everything much faster than we ever could. So, yeah, not that exciting. But now we have a section that it's filled with word problems on engineering and physics and a whole bunch of concepts that we actually see. And finally, we can see how calculus makes sense and why is it one of the pillars, the basic pillar actually, of all engineering and physics and chemistry and literally everything out there. Now, to observe this, we are going to first take a look at a square, and you can think of this square as made out of a very thin metal, and then you heat it up. What happens to metal objects when you heat them up? They do what?
Expand.
Expand. Very good. They expand. So I'm just going to show the expansion over here in blue and say let's make this square a little bit bigger. I could have just made the square bigger this. Well, let's make the square bigger that way. It's fine. There we go. So now, what happened with all of the measurements that we have? We have the side A. Now the new side A is larger. We have the area A. The new area, blue area, is larger. We have the diagonal D. The new diagonal D is longer. We have the perimeter P. The new perimeter P is longer. Literally, all of the concepts that surround the square grew in size, either length or area. If this was a three-dimensional box, you would have the edge grow in size, the volume grow, the surface area grow, the diagonal for each side or a diagonal of the box grows. So all of these concepts grew together. And since calculus is the science that measures change, we really want to study how these concepts change in relation to each other, which is why it's called related rates. Rates, as in derivatives taken in time. So rates is going to be derivative in time, because this expansion happens with time. It takes time to heat an object and for the object to expand. So you will see a lot of this around you. The objects heating up and expanding are something that engineers have to take into account when they are designing things. Here is an example. If you have ever been on a train, and I hope you've been on a train at least once in your lifetime and you paid attention, there is that sound that is always present when you are in a train. Tuck, 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 tuck. It's always like that. The pair, and then a little pause, and then another pair, and a pause, and it just goes that way all the time. Does anyone know where that sound comes from? Tick, 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 tick. Tick, tick,
If I had to
tick.
guess, it would probably be the wheels running over the individual rail segments.
you are very close. The wheels hitting the gaps in between rail segments. So what happens is the rail is very long, and then they put a little gap and another long rail. When the rail gets heated up in the summer, the rail expands this way and this rail expands this way, and they fill this gap pretty much all the way in the summer, and that sound is almost non-existent when you are on a train in the summer. But if you take the train in like December, that sound will be there and you will be able to clearly hear that, because the wheel that goes on the rail, and it's always two wheels, right, for the train. They're connected with all of those things, and then there is a car on it, right? Tuck, 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 tuck. See, the first tuck, the second tuck, 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 right? Oh, sorry, tuck, 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 right? It's the two tucks in the first one for the first two wheels, and then the second two wheels from the same car, they also go. So you have a tuck, 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 right? It's always there, and it's from there. You also have this notion of the bridge. When you go, anytime you go over those really, really large bridges, you will see those like this gaps in a bridge. That's the same thing. This segment of the bridge, now this is the bird eye view, right? So you're looking on the top, your lanes for your cars are here, and then you are driving, here's a car, and here's a car, and right car. There is this gap, an inch, 2 inch. It's computed, right? It's computed. That's what the engineer, civil engineer, has to compute this, because this segment of the bridge here will expand. This segment of the bridge will expand. This gap fills up in the summer, right? Because solid objects expand in the heat. All of that has to be computed. There are formulas, there are charts, there are things that you have to refer to as engineer. Otherwise, if you don't do that, you should look up the pictures online, what happens to rails where these gaps are not properly computed, and then they literally pop out and they twist like straws, these rails. And there are a couple of pictures online that you can find. Most of them are really old black and white photos, obviously, from the time when engineers were still trying to figure out all of these things, obviously. Anyway, so what is the big deal? What are we trying to compute and design and all of that stuff? So let's go back to our square and just take a look at the square and see that we have a side A. Let's say we have a perimeter P, we have the area A, and we have a diagonal D. So I can come up with the formula for area, which is A squared. I can come up with a perimeter formula for A. I can come up with a diagonal formula, which is root 2A. I use the Pythagorean theorem, right? And that's it, right? Those are the, let's say, those are the three formulas that I can observe. Now, what I can do is I can say that, all of these change in respect to time because the length, right, of one of the sides is growing, right? So if I take this formula for area and I take the derivative in respect to time, because the length of the side and the area grow with time, right, in time. It's not instant. We can come up with using implicit differentiation. Derivative of area is 1, but then you have to follow with the dA dt. On the other side, 2a dA dt. So I am taking the derivative in respect to time, And by our implicit differentiation section, we know that anytime when they don't match the variables, you have to follow with the chain. So that's where we got this dA dt each case. And now this formula here is known as related rates model. And it's a really cool thing because we can observe the growth of area in time as the length of the side grows in time. And it's related by whatever the formula has in between. So related rates, plural rates. Rate is a derivative. So the title tells you pretty much everything that you need to know. So now we have to talk about units. And the units are the ones that really help you understand what is given in the word problem, what you're looking for, and so on. So if you are familiar with any rudimentary physics, you know that length is given in, let's say, feet, and the area is given in feet squared, because area is found as length times length. So if length is in feet and the other length is in feet, then when you multiply feet by feet, you get feet squared. So length is just feet, and then area is feet squared. Now what I have here is feet squared per hour, let's say, feet squared per hour. And over here I just have feet per hour for this one. Now, what are they connected with? They're connected with number 2 that has no units to it, but there is A, which is length, and that's just feet. So you can see that feet times feet will make feet squared, and then you have the left and right side have the same units. That is absolutely a must when you are working with any kind of application or physics formulas or whatever. The units on the left and units on the right must always be identical. And if they're not, your equation is garbage. There is no talk about it, oh, it was a little bit off. It is a complete garbage. You either have the units match and everything be perfect, or a slight deviation from somewhere, it has nothing to do with reality. That is something that you have to be really careful about. Now, in math course, I mean, we just take the derivative, right? And I am talking about units because units really help you pick out what are the numbers that you are getting in the word problem. You are familiar with the units miles per hour. And if you use your brain for 2 seconds, you say, oh, miles per hour. Miles is distance, hour is time. Miles divided by time, distance divided by time. Oh, there is my equation for speed, right? Distance divided by time. Just by analyzing miles per hour. There is no nuclear physics surrounding that concept when you think about it. And this is why general chemistry is a joke as a course, because pretty much every single formula they have in that course is a triplet. If you have units, you just look at the units and you know every formula that exists in a course. In comparison to, obviously, physics, when you have a couple of terms and then they all cancel and so on. Most of the formulas in chemistry are strictly triplets. Very easy to work out. So now, what do I have here as a unit, right? What would I read this as? Well, I would say area grows in time at the rate of blah, blah, blah. There is a number there. See, area grows in time at the rate. So grows, it's positive, rate, its derivative, time, dt in denominator. All of these words have its meaning to come up with, right, to come up with correctly what it is. Over here, length grows in time at the rate of blah, 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 0.1 feet per hour, right? So the units will always tell you what your variables are. So if I am to say, if I am to see, without knowing the concept, the context of the question, without reading the question, if I see a unit, a number written as, let's say, 0.3 meters per second, I know that this is some kind of length. This has to be dA dt, dx dt, dr for radius dt, dd dt for the diagonal, dp dt for perimeter. It has to be any one of, it could be any one of these because I didn't read the question. I just saw the units. Because I see a division in a unit, I know it's a rate. I know it's some kind of derivative. If I see 0.3 m, well, then it's a, or it's x, or it's r, or it's diagonal, or it's perimeter, right? It's just length in that case. So the rate will always have a fraction, and the length, right, or whatever single, right, unit will only have no fraction, right? It will be just a unit there. So now, if I am to see 0.3 meters cube per hour, I immediately know that's dV dt, because meter cubed, that's volume. What we have here is meters, length. Go ahead, put feet, I don't care. Meters squared, area, meter cubed, volume. Because the meter cubed is meter times meter times meter. That's, right, 3 dimensions in space, one for x, one for y, and one for z. And that's, each one is given in meters. So it's meters cubed for volume. It is insanely easy to work through these concepts once you understand units, and then to read those problems and pick out what number goes where. Also, we'll see that we need to know this little bit so we can figure out what equation to write to begin with. So now I want to go back to my area equals a squared, then the derivative in respect to time of that equation was change in area in time is equal to 2a change of side of the length. I mean, the length of a side, there we go, in time. A related rates model. All I need to do is to plug in the numbers and compute whatever is asked to be computed. So for this formula, which is related rates, what I know here is the change of area in time related to the change of the length of the side in time as well. Another wording that quickly becomes very frequent in the word problems is to say, how fast is something changing? Yeah, fast, in time, right? How fast can you run? How fast can you get here? How fast can you read? How fast that and the fast is measured time. If I can solve, how fast can you solve the problem? Oh, I can solve the problem in 2 minutes. Great. I can solve a problem in 30 seconds, right? I am faster because we are comparing the times in which you can solve the problem and in which I can solve the problem. So that's going to be the rate of solving problem in time. So the fast wording immediately means the blah over dt. I should have put this in red so you know exactly what the word fast means. This is blah, blah. So how fast is the volume changing in time? How fast is the area changing in time? How fast is the distance changing in time? Hey, that's velocity. How fast is the velocity changing in time? That's acceleration. So every time you hear the word fast, it immediately means the derivative in respect to time. Now, all of the derivatives that we are going to have here are going to be derivatives in respect to time. All right, let's make some money. Usually I don't do the problems that are done in the book, but this problem is way too cool to pass on it. So here's the oil rig. And what happened is a little haboom on it. And now we have the oil spill spreads out into the ocean in this circular pattern because, right, it's a calm ocean. There are no currents, and the burst pipe over here that was taking the oil out is now pushing that oil and the oil floats on top of the water. So they have special ships to clean it up. It's not a very tedious thing to do because they have the specialized ships that do that. But the trick is that the longer you wait, the larger the area is for the cleanup. And we can use related rates to quickly understand how fast is the area of the how fast the area of the pollution is growing. And that's something that you as environmental scientist or a CEO of a company want to know, right? And so you can, right? I mean, you should immediately call up the cleanup crew. The faster they get there, less work they have. But you can compute how fast is this growing. Now, clearly, the oil spill is going to be on the area of these concentric circles that grow. So area of the circle, which is pi r squared, should be the common sense place to start because the oil floats on top of the water and it's in a circular shape, right? It's not spreading as a square around the rig, right? It's spreading in a circle. So we're going to use area of the circle. And because I want to study how fast is the area changing, I'm going to take the derivative in respect to time and come up with dA dt is equal to 2 pi r dr dt. You copy pi, derivative of r is 2r, right? Derivative of x squared is 2x. So derivative of r squared is 2r. But we also have to follow it with a chain because we took the derivative of r in respect to time. So now this is what we have. This is my related rates model that I can use to calculate, right? So this is related rates model that I can use to calculate how fast this oil spill is spreading away from the oil rig where we have a problem, where we have a leak. So now we can go in and take a look at the text, and it says an oil rig springs a leak in calm seas and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at the rate of 30 meters per hour, 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Radius of 100 meters, that is immediately clear. They said if the radius of the oil patch increases at the rate, the radius increases at the rate. We also see radius is a single length. I see a length over here. So it's just meters in the units they gave me. So it's length. The only length we have is the length of the radius. The other concept is area, and that's squared. So this has to be dr dt. If the radius of the oil patch increases at a rate, see the word rate immediately says it's a derivative. Now the other wording is how fast is the area increasing? Well, that was just the other way for us to say how fast is the area increasing, because it's going to be increasing in time and its area. So we are looking for dA dt. So dA dt is something that we need to compute, and luckily we have 100 to stick in here and 30 to stick in there, and that's it. We're done. So dA dt is 2 pi r is 100 and the dr dt is 30. Just plug the numbers in, right? That's going to be 6,000 pi. 6,000 pi. And then the units have to be meters squared per hour. So this is how fast the area, the pollution, is spreading. When the radius is 100 meters away from the rig, 100 meters is like 52 or 6'3". Trying to see if you are 6 feet tall, that's about 2 meters. So that's like 50 people stacked up, right, for 100 meters. I'm just giving you, if you don't know in meters, right, how far would 100 meters be, think about 50 people stacked on top of it. Each one of those has to be like 6'1" or 6'2", whatever the 2 meters is. Maybe 6'2", maybe it was 6'3", I don't know.
600 pi?
6,000 pi. 6,000 pi, yeah. Because we have 1, 2, 3 zeros. 1, 2, 3 zeros. So it's 6,000 pi. Pi is about 3. I know it's 3.14, but this is roughly 18,000 meters squared per hour. 18,000 meters squared. So, yeah. Oh, there's YouTube helping as well with 6,000 rather than 600. So, if I use the abacus and go 6,000 times pi, we get roughly 18,849,850 meters square per hour. So that means that in this hour, right? In the hour when radius was 100 meters, the affected area of the the polluted area, grew by this much. This is not the area. If you want to calculate the total area, you will just plug this in the area of in the area formula. We are not calculating the area. We're calculating by how much it changes. That's calculus. So you are calling the cleanup crew and you are screaming, get here as soon as possible because the area or affected area is growing by almost 20k meters squared per hour, right? So, wow. Now, what I want to do is just say, well, what if the radius is smaller, right? What if the radius is just 10 meters, right? What if r equals 10 meters rather than 100? Well, first of all, let's understand that the r dt is affected by how much oil is leaking. That's what's driving the r dt. Size of the hole in the whatever the oil is coming out from, right? So you don't change this, right? Because the oil is just going to keep pouring until you plug the hole. But what was the dA dt, right? It's 2 pi, and now it's 10, and then it's 30, and then now it works out to be 600 pi meters squared per hour. Come on, pen. Hour. There we go. And now that's about what, 1,1800, right? Because we're just knocking a zero down. Meters square per hour. So you see that the affected area is less, obviously, right? And we are keeping the same inflow of oil because we haven't plugged the hole yet. So it's important where you are measuring. That's why I did the second calculation as well. So we always have to specify where you want to measure, because the rate of increase or decrease will change when you change this particular observation. Now we'll see that in every problem we'll always have this part given to us as well. Now obviously when you are an engineer, you measure that, or you know what you're looking for, so it's still there. All right, next let's take a look at also one of my favorite problems, because we get to see a cool website. So we have an airplane flying towards the airport, and we have another airplane flying towards the airport. And these airplanes are separated by the distance d. Since both of these airplanes are flying towards the airport, when both of these airplanes get closer, what's happening with the separation between them, with the distance?
It'll be getting smaller?
It will be getting smaller, exactly. You can see that if you draw these lines like this, right, this distance is decreasing. We definitely do not want this distance to be zero, right? What is the distance zero between the two planes? What does it mean?
Crash.
Crash, exactly, right? Collision between the two planes. So we want to keep those two apart. Now, What is the really cool piece of information that we should have? We should know, right, how fast those two planes are getting closer to each other. So if I have one plane coming in and the other plane coming in, the distance between them is going to be decreasing. So I can use today's lecture, right, and the concept to write a mathematical model for that, and then we can later on program that in so computer can keep track for us, so we don't have to stare at the screen, you know, every second of our time, right? The computer will tell us. So, what geometry do you see on the screen?
Triangle.
Correct. What kind of a triangle?
A right triangle.
Good. Geometry is right triangle. And now the question is, for that right triangle, what are the formulas that you know about the right triangle? If this is the x distance going in, this is the y distance going in, what would be the formulas? Let's list all of the formulas you know for right triangles.
One of them is a squared plus b squared equals c squared. Just a quick
Perfect.
Pythagorean.
Yes, a squared plus b squared equals c squared. Okay, what else do we have for our right triangle? For any right triangle. What other formulas have you learned regarding triangles? What can we compute about a triangle? Guys, you just have a triangle.
Area equals half base times height.
Area equals 1/2 base times height. Thank you. What else can we compute for a triangle? Let's say you put sheep inside. What do you want to have?
Perimeter.
Perimeter fence, right? So A plus B plus C. Good. Perimeter. And then everyone is avoiding this one. We have 6 trig functions. Well, right? But for that I will need an angle. We're not going to use it in this example, but eventually we are going to use it. So these are the formulas that you know regarding the triangle. That's 9 formulas, right? 6 trig plus these 3. There are more, but these are the ones that that we usually. So now, what are the 2 formulas here that talk about lengths? It's a Pythagorean theorem and a perimeter. Now, these planes are not going to be flying around, right? So we're going to strike the perimeter formula down, and that leaves you with the Pythagorean theorem. So you start with saying that x squared plus y squared is equal to d squared, right? Because that's the hypotenuse, the longest side is d. And now you hit this with the derivative in time, because these airplanes are getting closer in time. We take the derivative, we get 2x dx dt plus 2y dy dt is equal to 2d dd dt. We can cancel these 2's. I divide both sides by 2. And you will have x dx dt plus y dy dt is equal to d dd dt. And at this point, you have your related rates model. This over here is related rates model. I would like to ask, what do all of these mean? What is x? Looking at the picture, what is x?
Distance for the plane to reach the
Excellent. Distance plane 1 to the airport. This becomes a plane 2. So that means that y is what? Distance plane 2 to the airport. Great. What is distance d?
The shortest distance between the two planes.
Good. So this is distance between two planes. Good. What's dx dt?
The distance over time.
Which is what?
The distance from plane 1 to the airport over the time.
Careful. X is the distance. What is dx dt?
Derivative.
Yeah, it's derivative, but what is it measuring?
Yes, miles per hour.
I can't hear you. You were too quiet.
I'm not sure. I
Not
thought
sure.
miles per hour.
Aha. So what is the miles per hour?
It's the rate at which plane 1 is moving.
Yeah, and let's put that, use a different word that everyone understands instead of word rate.
Velocity.
Okay. Yes, velocity, speed. Speed of plane 1. This speed of plane 2. And this is the rate, speed of two planes getting closer. And that's the scary one, right? That's the one we keep track. We keep track of the distance between the planes. That's given in miles. And we keep track at how quickly those two planes are getting closer. Guys, it's not enough just to say, oh, those two planes are 100 miles apart. We don't have to worry about it. Yeah, you have to worry about it if each plane is moving at 300 miles per hour. You don't have 7 days to figure out their altitudes and who lands first and all of these kind of things. If the two planes are 100 miles apart, which for you sounds like an insane distance, because New York is what, 60 miles from here, and it takes you an hour to drive. Imagine if you were driving to New York at 300 miles per hour, right? That is the speed at which, right, you're gonna get there in what? 300 is 5, so 60 divided by 5, you're gonna get there in like 10-12 minutes, right? So you cannot just look at one variable d and say, yeah, they're 100 miles apart, so don't worry about it, because the distance is closing in, and this one tells us how fast that distance is changing. So we need to know that one as well. Now, you can go and take a look at whatever problem and pick out the numbers. So if let's say x is 120 miles away from the 120 miles away from the airport. The other one is 150 miles away. Sorry, 180 miles away. And then the first airplane is going at dx dt, which is the speed of, and now I'm going to put this as a negative 150 miles per hour. And the other one is also going to go dy dt as a negative 225 miles per hour. Now you're going to go, why are those two negative? Well, the velocity is a vector, which means positive one way, negative the other way. And you decide what is the positive, what is the negative. Now on a highway, obviously, moving forward is the positive direction. And you do not want to drive backwards on the highway, even though I witnessed some idiots, already a few times, backing up on a highway because they missed an exit. Like there is no other exits up ahead. So why are these negative? They're negative because the distance to the destination is decreasing. And these airplanes are going towards the airport, and the distance between the airport and the airplane is decreasing. So we are going to say that both of those together are decreasing, making the total d distance between them to decrease at all times. So all of these decrease that is present here is going to be making both of these numbers to appear negative. Now we know when you look at the reading for the speedometer, right, you are going 60 miles per hour, you are going 150 miles per hour, right? That's the speed, but then the negative is there because direction is also important here. You are getting closer to the airport. Both airplanes are getting closer to the airport. Therefore, they are both closing in the distance, and the distance between them is decreasing, so both numbers are negative. Now, we could have one airplane fly away, in which case that distance would be a positive distance then, right? Because that airplane would be going the other way. So now, when I have all of these numbers, all I need to do is to plug them in. Now, the problem is that I still have two variables. I have x, I have the distance, I have the speed, I have the distance and the speed for the other airplane, right? Those are either provided by pilots or use the radar to locate the planes, so we're all good there. The trick is that, and we know that we are calculating the change in distance between the two planes. So I must calculate d, and d is easy to calculate because we have Pythagorean theorem, right? So square root of x squared plus y squared, and that's going to be the values that we have, which is 180 plus 225, right? 225. And when you work this out, you get about 288 miles of separation d. So now you can plug all of these values in and compute dd dt. So what do you have? You have 288 times the dd dt is equal to 180 times the negative speed. Well, no, first one was 120. 120 miles away at negative 150. So that's this. Plus the other airplane is 180 miles away at negative 225 is equal to this. And now when you compute all of this stuff and divide by 288, you get that they are closing in and at about negative 192 miles per hour. So this means, guys, that the distance between the two planes is closing in at roughly 200 miles per hour. It is not something that you say, yeah, I'll deal with that later, or, it has to be observed at all times because these distances are closing quickly. And now you have your dt, and you can understand now that the two planes are physically apart 288 miles, and it's going to be minus 192 in this 1 hour of flight time. So as you can see, the distance is dropping down to about 90, right, 96 miles between them in 1 hour. So it's not like let's put it off to a side, we'll come back to it later, because within hour and whatever, less than hour and 15 minutes, because you have to recompute, remember, when the distance is lower, when the distance is shorter here, when they got closer, you have to recompute the problem because you will have a different d at that point, because you have the different x and a different y giving you a different d, and that different d will give you a different rate at which they're getting closer. So you can't use this information that we calculated here for the rest of the trip. That has to be constantly recomputed, because it tells you the future of what will happen within an hour of time if no changes are made to the flight patterns. And these things are very complicated. Now, very complicated because these were just two planes coming into the airport, and you track a plane, and we didn't even talk about the altitudes. We didn't talk about what we just did a two-dimensional problem here, which is just the lengths and velocities. Now imagine what happens when you put in all of the planes, right? And I love this part because we get to go to one of my favorite websites. It's called Flight Radar 24. And this website is, Zoom people can't see it. There we go. Can you all see the website?
Yep.
Yeah.
All right. So this website is tracking planes live. Right? Let's go to United States. This tablet doesn't have a lot of RAM, so all of this is, me running the streaming and encoding and software, and then now this is just really, really, really slow to load. But here is the United States coming up, and you can see and guys, this is the air traffic now with the pandemic, that technically there are no flights in the air. This was really, like, you couldn't even see the land from the amount of planes that were displayed on the screen when it was last year, business as usual. This is not loading. I'm hoping that this will load soon. Come on. They're slowly coming in. You are getting some idea of what it means to come up with all of these calculations at one time, right? To track all of these, almost 10,000 planes that are in the air, right? And many of them need to land. Some of them need to have emergency landing. You can see, look at the Chicago airport, top left. You can see the New York here on the right hand side. Newark, New York, and LaGuardia, like three large airports in the New York area and then Chicago area. You can see, I mean, the DC area, it's a lot of planes. You do not, right, let a Joe sit there and crank this by hand, right? This is where the computer science majors kick in with their linear algebra and write the code that tracks, calculates what we did, but not just two-dimensional, right, between two planes, but calculates this between as many planes as are coming in at the same time, and assigns the flight order automatically and all of that kind of stuff. So we know, right, what is going on. So it's a lot of work. All right, let's go back to our problem. So take a look at Flight Radar 24 when you have the chance, and it's really cool thing. I have to shut that website down because it's really slowing the. There we go. All right. We used right triangle geometry to figure this out, and we are done. Now I want to show another application. It's again going to be a triangle. It's again going to be speeds, but this time it's going to be a little bit different, which is why you have to be very careful about certain things. So here is the house. We'll put the window over here. We'll put the doorknob, and then we're going to put the gutter right here. We're going to put the ladder, which is a 25 feet long ladder. There is a distance X and distance Y, so you do see your right triangle again. I'm gonna put Mark over here on the ladder. He is cleaning the gutter. Let's make him into a cowboy right here. There we go. Perfect. And he is happy because he's cleaning his gutter. Now, Joe comes along and kicks this one off, sets up the cell phone for the movie and so on, and kicks out the letter on this side, dx dt, out. So as Joe kicks this side of the letter this way, what happens with this side of the letter on the other side? Anyone? A wild guess?
Gonna fall flat.
Yeah, it's gonna fall down at dy dt speed going down. Is this the same problem as before? Yeah, except this time you don't have that distance d decreasing. That's now fixed. You see, before you can have the planes going either way. Now, if you pull the letter away from the building, from the house, the other side of the letter has to go down. If you pull this side of the letter in, the other one has to go up. Well, that should be common sense for all of you because you're just alive. And you've been around for whatever amount of years. And the reason why the letter behaves that way is because it's one solid 25 feet long letter. So it can't go in and down at the same time. Airplanes can go towards and away, and then one towards and one away in terms of the airport. But the letter is fixed. So now when I write my x squared plus y squared equals to 25 feet squared, you see that we have a constant here. And now when I take the derivative in respect to time, we just have our 2x dx dt plus 2y dy dt equals to 0. 2's will cancel when you divide everywhere by 2. And you have that x dx dt plus y dy dt is equal to 0. So now you want to know how quickly the letter is going to fall, right? Which is dy dt part. So you solve for dy dt. That's y dy dt equals negative x dx dt. Divide both sides by y, so that goes right there. What do we see? Right? We see that dy dt is negative going down. So this negative here is technically, all of this is a negative number. So dy dt is equal to a negative number, meaning it's going down, because dx dt is positive because it was pushed away from the house, making more distance. The distance grew as a result of dx dt pushing away from the house. Now, there I say clearly, if you push the letter this way, well, then the letter goes the other way, so there will be a negative number. And then that negative and this negative would make dy dt to be positive, which pushes it up, which makes sense. If you push this way, the letter pushes up. If you push that way, the letter pushes down. So these signs are really well understood when you observe this problem. Now the question is, do we know how much velocity Joe used to kick the letter out? You can say he did it at 2 feet per second. And if you have that piece of information and you can measure how far this x is, because Mark put that letter up 4 feet away from the house or whatever, you can, or I don't know, 6 feet away, whatever, doesn't matter what numbers we use. You can use your Pythagorean theorem to figure out why. Because look, you have your x is equal to 6 feet. You have your dx dt to be 2 feet per second. I'm just making these numbers up now. And I need y. That's the only thing that I need. And then I can plug those 3 numbers in here and come up with what I'm looking for, which is dy dt. So I can use x squared plus y squared equals 225. No, sorry, 25 squared is 625. And then you put this x in here as 6, and that will give you the y. Plug in 6, plug in 2, plug in whatever y you get, and there's your dy dx. So it's again a right triangle formula. It's again, right triangle geometry. It's still Pythagorean theorem, but this time the distance d was fixed because it's a ladder, and we see that when we write these equations, it 100% matches the reality and physics of what we have. We'll have to finish this lecture next class, because I still have one more triangle problem, and then we can move on to volumes. But we only have another 16 minutes left. So I'm going to do one more triangle problem, and then next class, in a part 2 of related rates, we'll deal with volume problems for a cube and a sphere and a cone and all of that, cylinder, right? So those will be, let's put the volume in a separate lecture. So now one more problem over here, and that problem is going to be a design problem. I usually say this, that if you have never watched the SpaceX launch, I have no clue why are you taking Calc 1, because that should be by default the most amazing thing around. It has all parts of engineering in it. The electrical and mechanical and the programming, right? And then you have the material science, like literally everything, chemistry, everything is involved. Civil engineering to make the ramps and the whole thing around the launch site. So every branch of engineering in existence is used to put the rockets together so you can shoot them in space. And as I said, right, if you are not interested in that kind of stuff, at least to see, I have no clue why are you taking Calc 1 or have any hopes of being any kind of engineer. Anyway, why am I talking about this? I'm talking about this because I want to design a camera that will automatically record the launch. I don't want a Joe holding it because his hand is going to shake and we're going to have the shaky footage. So I want to have a camera on a tripod somewhere, some distance away from the launch site. We're going to have the rocket, right, shoot straight up, and this camera is recording first at angle like this. Now remember, the camera records, it's not recording on a straight line. I'm just going to make the camera in line with the rocket, and then as the rocket takes off, covering, right, this height edge, the camera is supposed to swing with the angular velocity omega so that this middle line keeps following the rocket as the camera swings upward on this hinge right here. And what I want to design is electric circuit that will control the servo motor to rotate the camera the appropriate amount. So I'm just going to get rid of a few of these lines here, and as we can see, we have the same idea as before. Now I'm going to put this, let's put it 1,000 feet away, let's say, and this is going to be our angle theta, because remember, I need to rotate the camera up, and rotation is done through the angle. So in this point in time, I have this length over here, this length over here, and this angle over here. What right angle, you see that right triangle here? So what right angle triangle concept I am going to use to put all of these concepts together? Are we going to use Pythagorean theorem now?
No.
No, we're going to use trigonometry.
We're going to use trig, yes. We're going to use trig because there is an angle there. And what is which one out of 6 are we going to use here?
Tangent.
Excellent. Tangent theta is opposite over adjacent. That's it. So now, when I have my formula, I'm going to differentiate that in time. I'm going to differentiate that in time because I want to relate the speed of rotation to the speed of the rocket, right? So let's see. Taking the derivative, what's the derivative of tangent? Very good. And then we have to follow with d theta dt because we took the derivative of theta in respect to time. That's not the same variable, so we have to follow with the chain, implicit differentiation, right? On the other side, we have 1 over 1,000. That's a constant. And derivative of age is dh dt. What is dh dt?
The height and
What is it?
I forgot.
Well, what's age?
That would be the height of the rocket, right?
Age is the height of the rocket. So what is the dh dt then?
The speed of the rocket?
Speed of the rocket. How fast is height changing in time? You're going to cover miles in hour. So miles per hour is the speed. So dh dt. Now, those of you who did watch SpaceX launch, they put two dials over here. One is for altitude, one is for speed. We'll come back to that later. All right, cool. So all I need to do is to put my d theta dt alone. Secant going to the other side becomes cosine squared. Because when you put secant, it's going to be 1 over secant squared theta. And 1 over secant squared is cosine squared. Right, so turns out into a cosine dh dt. And this is the omega, the angular velocity at which the servo motor is supposed to spin to have the rocket in the center of the shot at all times. Now, please note that it's going to start turning quickly and then it's going to slow down and slow down and slow down because the rocket is further away, and when rocket is further away you don't need to turn so much because, right, the rocket being further away, there's just more for that shot. There's more distance. Anyway, so now the only thing that we need to do is to get rid of this cosine theta. So now this is computer science now, what I'm doing, because it's the computer science person that is supposed to program the controller for the servo motor, right? So you're writing the code for that. Yeah, electrical engineers do it as well, but whatever. So I have to read the cosine, and the cosine is the adjacent and the hypotenuse, but I don't have the hypotenuse here. So hypotenuse is going to be 1,000 square plus h square root of that, right? That will be my hypotenuse because it's the Pythagorean theorem that calculates that side. So my omega is going to be cosine, which is 1,000 divided by, remember, cosine is this divided by that. So it's going to be 1,000 divided by square root of 1,000 squared plus h squared. And I need to square all of this because the cosine was squared. And then I have 1,000 here and dh dt. So the only thing I need to do is to clean this mess up and we are done. So I'm going to keep this as 1,000 squared. And then the square root kills the square. So we have a 1,000 squared plus h squared divided by 1,000. I'll put divided by 1 so it's easy for us to see the calculation there. So angular velocity omega is going to be, this one cancels with that, and what you get is 1,000 divided by 1,000 squared plus h squared dh dt. So here is your angular velocity, which is, I used what we use in physics, but d theta dt, which is change in angle in time. And that's what your rotation is, right? Because you change the angle in time, you rotate the object for a certain angle. So we have the formula, and this is the formula that you plug into your controller, and look what you're getting as input: the height and the speed. And as I said right earlier, if you watch the launch, right, there's a rocket there flying, right, there we go. What you got over here are those two gauges. One shows you the height, the other one shows you the speed of the rocket. So as you are continuously feeding those into the formula, computer science person is programming this into the controller. Controller is giving electrical signals down to the servo motor. Servo motor is turning for the amount that is, right, electricity, whatever electricity is provided to it, it's going to spin, and that's what spins the camera. So now the camera can go and follow the rocket, and it has it perfectly centered in the middle of the shot every time, without, you know, anyone holding and shaking the camera and all of that stuff. So it's a really cool engineering feature, and you see it takes, you know, even to design something like that and make it into a prototype, and, you know, it takes time. You're not going to, you know, do this by trial and error when it's so easy to compute few things and program it in. I mean, you just need a live feed of height and the speed, and they feed directly into those two variables, and you're done, right? So the motor will give appropriate values, and controller will give appropriate values so the motor can spin, and the motor spins either directly the camera or the gearbox that eventually, you know, turns the camera. So we're going to stop here. Part 2 coming up on Monday. We are going to talk about the volume, so which is again important. We'll see storing the objects, and like, let's say you're making a conical pile, you put the gravel or corn on a pile. It makes the pile, it looks like in the shape of a cone. Drinking soda out of the soda can, that will be a cylinder. Rolling the snowball down the mountain, creating that huge snowball, that's going to be change in volume, right, in respect to the radius as well. So a lot of really cool volume problems in the second part. And we're going to learn a simple way to categorize all of the volume formulas, so you don't have to go back and memorize them all. If you know the way to compute them all, or develop the formula by yourself, then you're saving yourself a lot of time. And I'm going to demonstrate that as well. So we're going to put all of the formulas and concepts that you might need going down, especially you will definitely need in Calc 3, but whatever. We're going to write down the formulas, categorize, and say this is the way you remember all three, and then just need to fill in the blanks depending on what you have. But we'll deal with that next class on Monday. I'm going to switch now to office hours. So if you guys have any questions, please follow me there. We're a little bit behind with all of this stuff, right, with my internet outage, but luckily we had everything working today. You can also watch the other related rates from before, you can learn more. and I'll see if any one of you has a question. I will see you in Zoom during the office hours. Bye.